Module 1 covers OBD background, system highlights, system standards, DTCs, MIL, PCM and DLC, and trips and drive cycles. Computerized engine controls were appearing under the hood of many vehicles produced in the late 1970s. It would take several more years before the manufacturers supplemented the new technology with onboard diagnostics, or OBD. Technicians were often forced to rely on educated guesswork when diagnosing drivability problems, since they were unable to acquire data from the vehicle's onboard computer. The situation began to change in 1980. Manufacturers began to equip some of their cars with onboard diagnostics, which finally made data acquisition possible. OBD was designed to monitor specific engine subsystems, store fault codes for components not operating within prescribed limits. Technicians could retrieve codes by jumping specific terminals within the diagnostic connector and observing the flash sequence of the check engine light. Once scan tools became available, the diagnostic connector became a portal into the puzzling world of PCM inputs and outputs, enabling diagnostics to become turnkey for the diagnosing technician. In 1980, CARB, the California Air Resources Board, drafted regulations requiring all 1998 model year and newer vehicles sold in California to have OBD diagnostic systems. Although OBD systems before 1988 satisfied the requirements specified by CARB, the OBDII mandate ensured that every manufacturer's system had a dash-mounted warning light and the ability to detect failures in the following four areas: fuel metering system, primary sensor signals, EGR system, and computer. OBDII was only required to detect gross system failures, such as an open or shorted sensor circuit. A vehicle could emit excessive pollutants without the warning light coming on or a code being stored. Other shortcomings of the system included the inability to spot misfires, evaporative emission leaks, or a degraded catalytic converter. OBDII was a vast improvement over the black boxes of the late 70s. The system fell short of air quality goals, not to mention serviceability. As a result, the California Air Resources Board developed new standards for onboard diagnostics in 1989, which eventually resulted in OBD2. In 1989, CARB continued its work by laying the groundwork for OBD2, that's Onboard Diagnostics Generation 2. The Clean Air Act amendments of 1990 directed the Environmental Protection Agency, or EPA, to become involved in OBD2 development. EPA adopted the OBD2 standards established by CARB for model years 1994 through 1997. This included a 2-year phase-in period of 1994 to 1995, with full implementation required by 1996. For 1998 models and beyond, the EPA imposed a new 50-state standard. This combined the original CARB requirements along with the EPA's specific OBD2 regulations. Pre-1996 systems included most of the OBD2 functionality. However, they generally were not equipped with an enhanced evaporative emission system. This is also true of some vehicles built after 1996, since full federal compliance was not required until 1998. OBD2 is more than just an OBD1 system with a software upgrade. OBD2 systems use sequential fuel injection along with multiple heated oxygen sensors. In addition, the OBD2 computer, known as the PCM or Powertrain Control Module, is designed to handle nearly 15,000 new calibration constants. While it's not a specific requirement, many OBD2 systems are equipped with both a MAP, or Manifold Absolute Pressure sensor, and a MAF, or Mass Airflow sensor, for monitoring engine load and airflow. In addition, the evaporative emission system contains devices specifically designed for conducting leak and flow tests. With OBD2, trouble codes are not based solely on gross failures, as was the case with OBD1. That's because OBD2 is designed to turn on the malfunction indicator lamp, or MIL, when the performance of an emission-related system or component, or catalyst, has deteriorated, rather than wait until it stops working altogether. In fact, OBD2 will turn on the MIL anytime emission levels exceed 1.5 times the Federal Test Procedure, or FTP standard, or catalyst damage or degradation occurs. To accommodate the increased processing power required to monitor the operational efficiency of individual systems and components, OBD2 PCMs are significantly larger and more powerful than their OBD1 predecessors. The Society of Automotive Engineers, or SAE, has developed numerous guidelines regarding diagnostic information and OBD2 functionality. The EPA adopted the following SAE standards as part of the federal requirements for manufacturer compliance. SAE Document J1850, title, Class B Data Communication Network Interface. Serial data transmitted between the PCM and a generic scan tool is known as Class B data. J1850 establishes several protocols for the transmission of Class B data. SAE Document 1930, title, Electrical Electronic Systems Diagnostic Terms, Definitions, Abbreviations, and Acronyms. Subject, Common Technical Language. The standard establishes common terminology for electrical electronic components and systems used by vehicle manufacturers. Prior to J1930, manufacturers assigned unique terms to their vehicle's engine control and emission-related components. SAE Document 1962, titled Diagnostic Connector. Subject, Design and Location Uniformity. The standard establishes the design and location of the data link connector, or DLC. The connector must have a common 16-cavity configuration, including 7 that are defined by the SAE, common to all vehicles, and 9 cavities reserved for the discretionary use of the vehicle manufacturer. In addition, the DLC must be located close to the instrument panel within an area extending from the driver's door to 12 inches or 300 millimeters beyond the vehicle center line. The DLC should also be visible to a crouched technician when the driver's door is open. If the DLC is located out of this line of sight, a sticker should be evident indicating the connector's location. SAE Document J1978, title OBD2 Scan Tool, subject Scan Tool Performance. The standard establishes the minimum requirements necessary for a scan tool to become OBD2 compliant. In addition to mating to the 16-cavity DLC, the scan tool must be able to automatically determine the vehicle's communication protocol, as well as display and clear diagnostic trouble codes and freeze-frame data. Additional requirements include the ability to display current data parameters, along with other emissions-related information, such as the readiness status of the diagnostic monitors. SAE Document J1979, titled Electrical Electronic Test Modes, subject is GST Diagnostics. The standard defines the operating test mode requirements for scan tools. These requirements include the ability to gain access to specific data as well as perform certain functions. SAE Document J2008, titled Recommended Organization of Vehicle Service Information for Interchange, subject Service Information Availability. The standard establishes guidelines for the distribution of technical information from vehicle manufacturers to the aftermarket repair industry. The EPA requires all 1994 and later emissions-related information, including reprogramming events for passenger cars and light trucks, to be available to the aftermarket and sold at the same price offered to factory dealerships. Any non-emissions-related information made available to the aftermarket must be sold at a fair and reasonable price. SAE Document J2012, titled Recommended Practice for Diagnostic Trouble Code Definitions, subject Common Failure Codes and Code Definitions. The standard establishes a universal code format along with common code definitions for emissions-related failures reported by the PCM. OBD2 trouble codes, known as DTCs, consist of one alpha character followed by 4 digits. Prior to OBD2, manufacturers used their own unique codes and definitions for identifying malfunctions in the engine control system. This complicated the diagnostic process for technicians. Under the OBD2 requirements, SAE Standard J2012, all emissions-related faults are assigned universal 5-character alphanumeric codes along with common definitions. Additionally, all codes on vehicles with OBD2 use the same 5-character format and go by the term Diagnostic Trouble Code, or DTC. The DTC format consists of one alpha character followed by 4 digits. The alpha character identifies the area of the vehicle where the malfunction was detected. This includes B for body, C for chassis, P for powertrain, and U for network. The first digit of the DTC indicates whether the code is generic or manufacturer-specific. Generic codes, indicated by a 0, are authored by the Society of Automotive Engineers, or SAE, and apply to all vehicles. The second digit, 3 in the DTC, identifies the particular system experiencing the problem. For this example, 3 identifies ignition or misfire, while the remaining 2 digits, 40, correspond to a specific code definition. In this example, 40 identifies a CMP sensor performance problem. So, the last 3 digits in the DTC indicate the vehicle system, 1 through 7, and the code definition, 00 through 99, as indicated below. The code for air and fuel induction, 100 through 199. For fuel injection, 200 through 296. Ignition or misfire, 300 through 389. Auxiliary emission controls, 400 through 474. Vehicle speed, idle controls, auxiliary input are 500 through 573. Computer inputs and outputs are 600 through 606. And transmission transaxle are 700 through 790. With OBD2, failures detected in computer-controlled systems fall into one of 4 categories. Emissions-related failures are categorized as Type A or Type B, while malfunctions unrelated to the emissions control system, such as ABS failures, are designated as Type C or D. Be aware that the malfunction indicator light will only respond to Type A and B failures. Type A DTC, an emissions-related failure involving certain misfire detection, fuel control, and comprehensive component monitor tests. After the first occurrence of a Type A failure, the PCM will store a hard DTC, or Diagnostic Trouble Code, eliminate the MIL, and store corresponding freeze-frame data. The PCM's response to a Type A failure is known as one-trip detection logic. A Type B DTC is a category of emissions-related failures considered less serious than those designated Type A, or when emissions exceed 1.5 times the FTP, that is, Federal Test Procedure Standard. When a Type B failure is detected on the first trip, the PCM will store a pending code but will not activate the MIL. If the failure reoccurs on the second consecutive trip, the PCM will illuminate the MIL and store a hard DTC along with corresponding freeze-frame data. The PCM's response to a Type B failure is known as two-trip detection logic. Type C DTC. Failures designated as Type C are not related to emission systems or components. Consequently, these malfunctions will not trigger the MIL. Instead, a Type C failure will cause the elimination of a specific service light, fuel cap, or fault message, depending on the vehicle, after the first occurrence. In addition, a hard code will be stored by the appropriate onboard computer. Type D DTC. Failures designated as Type D are not related to emission systems or components. Unlike Type C malfunctions, a failure categorized as a Type D will not trigger any telltale lights. However, a Type D failure will cause a hard code to be stored by the appropriate onboard computer following the first occurrence.